2, 1.
Welcome to session 3 of the webinar series on challenges, lessons, and innovations in integrated flood risk management. This is an event organized as part of the Asian Development Bank's Knowledge Support and Technical Assistance Project, Strengthening Integrated Flood Risk Management. I'm Lorena Ramirez, Senior Water Specialist from London Mills and the Project Manager, and I will be moderating today's session. Please note that this meeting is being recorded. Therefore, turn off your cameras if you wish. Please also note that there are 2 language channels providing simultaneous interpretation to Bahasa and Vietnamese. Next slide, please. This webinar will last for 90 minutes, which will include a discussion and Q&A section at the end after the presentations. Please submit your questions during the session via the chat box, and we will compile them and go through them at the end. Before moving to the presentations, we will start the session with opening remarks from the team leader of the Knowledge Support and Technical Assistance Project on Strengthening Integrated Flood Risk Management, Ian Wood. Ian has over 35 years of experience working in the water resources and flood management sectors, and over half of the experience has been in Southeast Asia. Through working on projects with donor agencies, Ian Wood can offer some insights on the many practical aspects for implementing flood risk and disaster management programs. Over to you, Ian.
Thank you, Lorena. So welcome to everyone. So as Lorena explained, so this webinar series is part of this KSTA with ADB on strengthening integrated flood risk management. The TA is being implemented by Landell Mills and JBA Consulting, both from the UK. Obviously, our client is ADB, but the funds for the project itself are coming from the Urban Climate Change Resilience Trust Fund, which is a trust fund providing grant funds supported by the Rockefeller Foundation, by the government of Switzerland, as well as by UK aid as well. The TA commenced 3 years ago in February 2019, and it concludes later this year in June. The overall scope of the TA has been 8 countries that are part of the Urban Climate Change Resilience Trust Fund scope, which is Indonesia, Philippines, Vietnam, Myanmar, Bangladesh, India, Nepal, and Pakistan. So the overall objective for the TA has been to strengthen the design and implementation of IFRM solutions, as well as enhancing knowledge and application of IFRM strategies. And so in that, there's been three outputs. And the first output is about knowledge. And so this activity is about, that we're doing today, is about knowledge. We're talking about sharing the experiences and lessons learned from various issues for IFRM. A second output is about was assessment and looking at these 8 countries and conducting some sector assessment of flooding issues at various types and various formats. And then thirdly, the third output has been about specifically supporting with preparation activities supporting ADB projects in these 8 countries. And in particular, this presentation talks about activities done specifically in the Philippines and in Pakistan relevant to coastal management. So we haven't done every aspect of IFRM in every country. It's been an on-demand type process. So in this case, there was particular activities relevant in those 2 countries, Philippines and Pakistan, for flood risk management. If we go to the next slide. Well, I think that's you, Lorraine. I think I'll hand back to you then. Okay.
Thank you, Ian, for your words and introduction. Next, I would like to introduce the speakers of today's session, Faye Luxford and Blair Spendlow. Faye Luxford is a senior coastal flood risk analyst with over 11 years of professional experience designing and implementing methodologies that use the best available stream value statistical techniques and oceanographic models to assess coastal flood risk. Faye has worked assessing the flood risk from storm surges, tides, and waves from tropical and not tropical storms in the UK, Australia, Canada, Vietnam, Philippines, and Pakistan. The second speaker of the day is Blair Spendlow. Blair has a master's degree in both physical oceanography and in economic policy. He has a wide range of experience in terms of environmentally sensitive design of resilient coastal infrastructure, mid-ocean design, and coastal flooding. Blair has been involved for several years in Singapore's nationally significant climate change work, involving design elements utilizing hard and soft interventions for coastal protection, managing the design studies for the restoration of Singapore's largest mangrove tract. He has significant experience on best practice approaches for marine environmental impact assessment, as well as modeling natural-based solutions. Hi, Faye and Blair. I'll pass it to you for the presentation. Thank you.
Thanks, Lorena. So I'm going to start by giving you an overview of how we've broken down our presentation. So we'll start with why is coastal flood risk important? Then we'll give an example of coastal flood risk analysis and benefits of nature-based solutions. Next, we'll talk about coastal data challenges and lessons we've learned through the project. And we'll finish with the capacity building we did. Could you go to the next slide for me, Blair? So before I jump into the presentation, I'd like to give you some background on our project. Ian mentioned it, but we analysed the coastal flood risk in 2 locations. So the Indus Delta in Pakistan and also 2 locations in the Philippines, Halaor and Iloilo. So therefore our examples are based on these 2 locations. So why is coastal flood risk important? I'll just go to the next slide for us, Blair. Thank you. This image shows destroyed houses in Tacloban, the Philippines, after Typhoon Haiyan in 2013. But unfortunately, it's possible to find many similar images from around Asia, and notably, I'm sure we all remember the 2004 Indian Ocean tsunami. Coastal flood events tend to be quite short, maybe compared to like riverine events, but in the case of Tacloban, you had a 6-meter storm surge that then pushed up to 2 kilometers inland. And as it comes in, it's obviously killing thousands of people, injuring many more, destroying properties, infrastructure, livelihoods. This type of destruction we obviously want to avoid. So what areas are vulnerable? Can you just go to the next slide? Thank you. This map shows, this map is of 2013, which I've taken as an approximation of the present day situation. We're going to talk later about the importance and impact of different methods and data sets to identify vulnerable areas, but for now I'm using climate central data with the exact details in the top right. This figure shows land expected to flood on average once a year in 2030. Obviously, the areas vulnerable to coastal flooding are low-lying coastal areas, but I've zoomed in some of these areas. So you can see here Bangladesh and West Bengal, and then also you can see the Red River Basin southeast of Hanoi, and a huge area of land south of Ho Chi Minh City in Vietnam as well. So these are large areas of land that are at risk. So I've touched on it there about data sources, and we'll talk about more later on as well. But as an example, here are two very reputable data sources that have totally different answers. So in these two images, you're seeing one image on the left from aqueduct floods, and on the right, you're seeing a climate central image of the same area in Vietnam, south of Ho Chi Minh City. So the things that are similar about these two images, they're both showing you a 10-year flood in 2030. They're both using the same climate change scenario and the same extreme sea level data set, and they're also using the same method to create the flood map. So they're using GIS-based projection modeling of flooding. The big difference between the two data sets is that the aqueduct product has used the merit DTM, whereas the climate central has used the coastal DEM. You can see what difference that makes to where they assess as being at risk. So it's probably a bit obvious, but yeah, the key to assessing coastal flood risk is you have to know the level of your land relative to mean sea level, which is what's the difference between merit and climate central. So we're going to do our first poll now, and I'm going to hand over to Blair once I've done it. So could we bring up our first poll, please? So the first poll is, what is driving changes in coastal flood risk in your country?
Thanks, Faye. And thanks for that introductory section. I'll be taking over a small section of my own shortly, but we'll just give everyone a little bit of time to consider this poll question and the answers. The possible answers being urban expansion in coastal cities, so increased exposure to hazard, sea level rise, which I'll be talking about shortly, changes in tropical cyclones, which is a topic of discussion in the literature, and subsidence, the land actually getting lower relative to the land. Could we close the poll now, Catagonia? Okay. That's disappeared from my screen, but I think it showed 40% of people suggesting that exposure, especially in urban areas, increased exposure. So people moving into vulnerable areas drives a lot of the coastal flood risk in some of the countries that are represented in the audience. Okay, so I'll start my section talking about exposure, which follows on nicely from that poll. So in terms of exposure, what we're looking at here is population exposure. And so with sea levels projected to rise by 2050, the sort of moderate projections are that the changes are enough to threaten land currently home to about 150 million people permanently in the future. These are people that will be in the future living on what will then be about the high tide line. So 150 million people, what is this quantum? 150 million people is around the population of Bangladesh, for example, which is the 8th most populous country in the world. 150 million people is about the combined population of the world's 5 largest cities: Tokyo, Delhi, Shanghai, Sao Paulo, and Mexico City. Within low-lying areas, it's also important to note that people living on river deltas are approximately 300 million. And so these people living in these low-lying areas, not only will they be getting their toes wet at high tide, but they also live in the latitudinal zone for tropical cyclone genesis. So they are more vulnerable to extreme sea level events as they occur with this rise in sea levels. And of all nations, with a total of at least 25 million people, Asian countries make up 9 of the top 10 most at-risk nations. And you can see a lot of that in the graphic here. The hot colors represent higher populations exposed, and there is a real concentration of that in Southeast Asia, especially in South Asia. In terms of the impacts of sea level rise and coastal flooding with respect to economic growth, sea level rise will lead to a definitive loss of land. Land, of course, being a natural resource that matters a lot for economic production. Some of the low-lying areas are actually some of the most economically productive. If a strategy of retreat is a preferred adaptation option, the value of assets and investments in that area that is being vacated decreases as the risk in the zone increases itself. So at the time that a zone is finally evacuated, the assets would be at the end of their lifespan and would therefore have zero value. So we need to start thinking now what we want to develop and what will be in the future vulnerable areas. Conversely, if a hold the line approach is the dominant paradigm, then this would result in significant capital and opportunity costs, disproportionately benefiting some private land owners, which is something we've seen in the past. Recreational assets may be replaced by protection structures, so we lose social capital. So we lose natural capital, but associated social capital with that. And as marginal and high-risk land continues to be developed in cities, as we noted before, the result will be increasing costs of temporary floods, and development pressures on the coastal zone will further increase. Sea level rise is inevitable. We've all seen graphs like this before. The changes that we're seeing at the moment are accelerating, and even if emissions stop now, sea levels would still rise for many decades to come. The distribution of, if we compare and contrast inland flooding with compared to coastal flooding, the distribution of changes in precipitation on the land, and therefore the resulting distribution of increased inland flooding is highly uncertain. Whereas relatively speaking, when it comes to coastal flooding, we know within a fairly narrow coastal band where we need to adapt and plan for sea level rise in the future. Another common graph that is displayed when talking of these matters, projections of sea level rise under different scenarios. We have a best central estimate here, we have an upper bound and a lower bound, and we have a scenario. This particular plot is actually from AR1 a few decades ago now. And what we see, what I want you to take note of is this upper bound line, which meets the year 2100 at a sea level rise of about 1 meter, slightly over. This was the conservative higher bound estimate from AR1. And when we compare this to more recent projections, it's important to consider that over the years, the models have improved, computers are more powerful, we have a more robust historical record to compare the models to. The way we assess future scenarios has changed. Representative concentration pathways have been replaced by shared socioeconomic pathways. The new SSPs offer 5 pathways that the world could take. Compared to previous scenarios, these offer a broader view of a business as usual world without future climate policy and with updated global warming estimates. And if we compare that same upper bound from a business as usual approach from AR1, it's consistent with more recent projections, but consideration now of more high impact storylines, as it said, may result in much more significant sea level rise. So coastal flood risk assessment is important for a lot of reasons, but the context in which we are assessing coastal risk is changing with respect to the science, the climate projections, but also in a particular location, exposure, socioeconomic factors, which mean that we sort of constant reassessment and evolving reassessment is necessary. So just a bit of data here, real data from Karachi, which will be the subject of some of my material later in the talk. So the Karachi tide gauge, this is the time series for 10 years. If you look on the left, this is the present day mean sea level. So a really high tide in Pakistan, Karachi at the moment, hits about 3.5 meters above a local vertical reference. This will happen, by the looks of it, you know, a few times a decade. We put 1 meter of sea level rise on top of that. That same elevation that would very rarely be inundated by the tide will virtually be inundated daily. If you put the tropical cyclone risk on top of that, then there's obviously much more frequent coastal flooding in our future. So some examples of analysis and coastal risk. So I just wanted to take a step back and think about the physical context in which we consider coastal flood risks. Coastlines are resilient when they're allowed to behave naturally. And while they are complex systems, the processes are well understood. When you stand on any given coastline, while the appearance of that coastline may be different compared to the next, what you will observe is largely a function of the energy regime, the nature of the sediment being supplied, and these factors. Coastlines are armored, even if it looks like they're soft, even if there is large volumes of sand or mud, which is dynamic and moves around. This creates some buffer capacity to protect from extreme events. Healthy coasts are usually in a state of dynamic equilibrium, so they fluctuate. But if they are in a healthy state, that adjustment will be cyclical, seasonal, and although there is dynamic changes, a shoreline will remain fairly stable. And it's protecting that natural or existing function or emulating it in terms of hybrid solutions, which is one of the key pillars for developing nature-based solutions at the coast. Coastal ecosystems are also regenerative, but not only that, green coastal assets such as seagrass, coral reefs, mangroves, wetlands, coastal forests also hold vast natural capital, serving economies, and they hold cultural value, and ensuring that that value is considered and accounted for in the development of options for coastal resilience is another key pillar of nature-based solutions. So this talk is largely about flooding, but I just wanted to take a step back and just highlight that coastal risk topics are more broad than just flooding. Coastal risk also exists in terms of erosion and at different timescales. Short-term erosive events may cause significant damage over the course of 24 hours and erode large amounts of sediment and reduce that buffer capacity. And if consecutive storm hits, that's when significant damage can occur. Long-term morphodynamics are affected by catchment land use, for example. And so changes we see on the coast are often linked to changes elsewhere in the system. Vegetation loss, of course, especially around mangroves, is a significant risk and problem. If we look at a more focused level on a particular piece of infrastructure, we're interested in coastal risk to help design resilient infrastructure, physically resilient, but also sensitive to the environment around it. Maritime infrastructure requires risk assessments and optimization of certain structures, which, for example, increase or decrease the downtime of a vessel at berth, for example. So I'm just going to show you two animations, which hopefully tell a different story about different approaches that we use at different scales to assess coastal flood risk. So in this example, we are resolving in very high detail wave structure and interactions, in this case, a seawall. And we're using engineered elements here. So with quite a high level of precision, we are expected to try to calculate the overtopping from certain offshore deep water sea states. So we transform the wave into a shallow water location and overtop the wave to try and calculate how much water is going to overtop, and we do so in very high resolution and very high accuracy and sophistication. But we do this at very localized scales. We would never try to attempt to do this for you know, a whole city's coastline, or even within a port at any one time. We're not necessarily going to model dynamically like this, the wave overtopping at every structure in the port. We focus on a small selected area. It's essentially a numerical experiment, and we carry those outputs into our detailed engineering design. On the other hand, when we're dealing with natural ecosystems and natural ecological assets, these structures are not regular. They often cover vast areas, and we're interested in assessing the risk mitigated by such ecosystems at larger scales. And the individual elements are not engineered, they're complex. They bend with wave and current and surge energy. So we can see that we don't attempt to assess these assets at the kind of detail that we would for engineered structures. And again, we're doing so at larger scale. So what is fit for purpose in a particular location is largely dependent on the application, the data available, and an understanding of what is reasonable to expect in terms of the confidence and accuracy you can gain from using a particular method. There's a well-known phrase by a statistician called George Box. He said that all models are wrong, but some are useful. This is what the phrase eventually came to, but earlier on in some of his writings, there's a couple of very nice phrases that came out of his writings, and I especially like the second one here. Since all models are wrong, the scientist must be alert to what is importantly wrong. It is inappropriate to be concerned about mice when there are tigers abroad. So later on, when I take the stage again, I'm going to talk you through some of the very pragmatic things that we did when we were modeling large-scale coastal flood risk in Sindh province in the Indus Delta in Pakistan, where we had a real lack of data. We were looking at large-scale flood hazard, the whole delta, about 250 kilometers. And really, we were concerned with identifying, understanding what might be importantly wrong, and making sure that those elements weren't negatively affecting the outcomes of our work. I'll pass it back to you, Faye.
Thank you. So now I'm going to talk about a key element of mapping flood risk, which is extreme sea levels. Just move on to the next slide. Thanks. I'll start by looking at components which make up extreme sea levels. So I'm going to focus in a section on extreme sea levels caused by meteorological events, and I'm not going to talk about tsunamis since they have totally different processes, but obviously they are a huge risk factor as well. So for more common storm events caused by weather events, oh, if you just go back for us, Blair. We've already talked about mean sea level and how that will change in future, but you also have seasonal to decadal variations in mean sea level, which are important in some regions. Tidal range is hugely important in some regions and much less so in other places. But storm surge is usually the biggest driver of extreme sea levels. So the next slide, we'll talk more about that. However, it depends on your location. In some locations, wave setup and wave run-up can be just as important as storm surge, or even potentially more important. So go to the next slide. Billy, if you could just go, thank you. So storm surges, like I said, are the biggest cause usually of extreme sea levels, and they arise from the inverse barometer effect and wind stress, with wind stress typically the largest component. So the inverse barometer effect elevates sea levels approximately 1 centimetre for every 1 hectopascal fall in atmospheric pressure relative to surrounding conditions. And the inverse barometer effect, it occurs in all locations the same, whereas that's not true of the wind stress. So wind stress directed onshore leads to an increase in sea levels, particularly within semi-enclosed embayments, or under severe wind stress, such as produced by typhoons. And under the same wind conditions, a coastline fronted by a shallow sea will experience a greater storm surge than one fronted by deep water, which is why if you've got to model a storm surge to get your extreme sea levels, you really need to know about the bathymetry in front of the coastline that you're interested in. And we'll cover that a bit more when we talk about data too. So next slide, please.
Hi, Faye. Sorry to interrupt.
Yeah.
Would it be okay if you turned your video off, because the signal keeps cutting a bit, so that might make it a bit better. Thank
Sure,
you.
I've just turned it off. Hopefully that will help. So I'm going to talk about 3 methods for calculating extreme sea levels, depending on what data you have available. So the first method we'll look at is extrapolating observations. So in the top left, you have an example tide gauge observations. And this is actually taken from the Karachi tide gauge. And you can see there you've got the astronomical tide, the full observed sea levels, and we've extracted the storm surge from that as well. So if you have long-term observations, you can use them to characterize everyday conditions and then fit an extreme value distribution to the tail and get extreme sea levels for different return periods. And the great thing if you do have the observations is the observations don't include any model error, so there's a higher level of accuracy in this method. However, the disadvantages are in most locations, you just don't have the observations to use. And where there are observations, the records are usually very short and then they capture very few events. So especially if you're in an area with typhoons, you need a really long time series. Otherwise, you're unlikely to get a typhoon observation in there or to get enough to do accurate extreme sea levels. And if you were to do this on a short time series, the risk is that you underestimate the extreme sea levels. So the second method, if you don't have observations, we'll just go to the second slide, is that you can extrapolate hindcast data. So it's the same as the first method really, but you're just replacing the observations with modeled time series of sea levels. An example of this is the Global Tide Surge Model Dataset. This is a model of tides and surges around the world. It was run for 36 years, and then they fitted a Gumbel distribution to the annual maxima. However, the authors acknowledge that 36 years contains insufficient numbers of typhoons to obtain reliable statistics of extreme values. So the image in this picture shows typhoon tracks from 1959 onwards that pass within 800 kilometers of the Indus Delta. And you can see there are very few observed events. So for this location where we were studying around Karachi, a 36-year hindcast would provide insufficient data on the storm surge risk. However, in areas not affected by typhoons, extrapolating hindcast data can work really well. It's great because there is data available globally. But obviously, because you're using modeled data this time rather than observation, the quality of your extreme sea levels is always reliant on the quality of that storm surge modeling. So the next method that I've put in discusses what to do if you do have a location which is affected by typhoons. And in this case, you need to generate a lot more storm surge data to base your extreme sea levels on. And that's what we did both in Pakistan and the Philippines. So the first step is to generate a synthetic typhoon data set. And then you model the resultant storm surge from them synthetic typhoons. And finally, you combine the storm surge data with mean sea level and tides to calculate return period sea levels. Let's talk about them 2 steps a bit more. So the first step is the generation of the synthetic typhoon dataset. So in this image on the right, I'm showing the dataset we used for Iloilo and Halaor in the Philippines. This dataset was provided by Pagasa, and we generated one ourselves for Pakistan. Both ourselves and Pagasa were using the Geoscience Australia's tropical cyclone risk model. So what this does is it takes the observed tracks and it creates a synthetic data set that's statistically like the input track data, but also has been extrapolated to more extreme events. And the data set we created represents 10,000 years of typhoons. So you can see the big jump up from a hindcast of 36 years to now we're representing 10,000 years to get enough coverage with enough different types of typhoons that we can have a good estimate of extreme sea levels in each location. And once you've got this synthetic data set of typhoons, you need to know what storm surge that is generated by each one, where the hydrodynamic modeling comes in. So in Pakistan, you can see an example on the right-hand side of the modeled storm surge along the Sindh coastline. There were just under 8,000 typhoons because it's not impacted by that many each year. So we modeled all of these in a telemark hydrodynamic model. In the Philippines, there's a lot more typhoons, higher frequency. So Pagasa were unable to model there's almost 20,000 typhoons. So instead they modeled a subset, and we used machine learning to emulate the storm surge for the remaining typhoons. So there's just a summary of 3 different methods you can use to calculate extreme sea levels depending on what data you have available. And I'll pass back to Blair now.
Thank you, Faye. Okay, so we've touched a little bit on some of the work we did in the TA. Faye's last section talked about developing these synthetic data sets, typhoon tracks for Philippines and the Indus Delta. So what I'd like to focus on now is the Indus Delta work. And again, it was spatially a very large area. And we had some real issues in terms of lack of data, but coastal flood hazard and risk is not well known, or not being well quantified on that scale in the past in that location. So for this initial assessment for project preparation for the ADB in this particular area, we basically had to play with the cards that were dealt and develop some pragmatic approaches for proving that the model was fit for purpose. So what I'll cover here is a brief overview of the data. We'll then go into delta morphology and how that affects our estimates on future coastal hazard. That links nicely into the concept of relative sea level rise. And lastly, I'll give you some examples of what the difference is between a bathtub approach versus dynamic modeling. I'll explain what a bathtub is in the context of coastal modeling at that stage. So this was our study area. Excuse me. It's the Indus Delta. And Sindh province sits at the bottom of the Indus River system, which extends some 1,600 kilometers to the north. The delta is an arid delta, which makes it interesting, and it has some significant mangrove tracts inside of it, some significant restoration efforts also in terms of those mangroves. But the distance across the study area is about 200 kilometers. So it is a vast area in which to look at large scale coastal inundation modeling. Up here in Karachi, basically the only data that we had at the outset of the work was one tide gauge, which I showed a time series of before, and Faye has showed small samples of in some of her material. It's a nice data set. It's continuous. It's fairly long relative to some other experiences that we've had. So it gave us a good data basis, but generally speaking, the data here is quite scarce. And if we zoom into Karachi, you can see, you might be able to make out some of the areas that are clearly tidally inundated in the mangroves. Tidal inundation extends at least 20 kilometers inland, and in some places up to 80 kilometers inland. Now, there's a real backstory here that we don't really have time to get into, but we used a fairly new terrain product designed for coastal flooding applications called Coastal DEM. It's based on publicly available SRTM data, which was the shuttle mission flown in around 2004, finally made available in 2014, I think, which gave for the first time a global high quality terrain, uniform consistent terrain data set. Coastal DEM was used for this location. Coastal DEM has been validated in different locations. So we were asked to show some evidence that Coastal DEM, this terrain data set, works for our study site. And we looked at different publicly available data sets, and we convinced ourselves that we were able to tell some sort of story about how good the data was in this location. And in doing that, we took some small sample sites. Here you can see an example of what we called site number 108 and site number 121. That's not really important, but what we saw in these locations was a little bit confusing. In some cases, it showed that the data was in good agreement with what we would expect the elevations to be. And in other locations, we saw positive and negative biases in the terrain data sets that we were looking at. And it wasn't until we mapped this in 2D spatially that we saw some patterns. And essentially what you see here is the blue areas are showing areas of terrain we think are higher than they were historically. And in the orange areas, generally, these are areas that we think the elevation has decreased relative to some terrain baseline we were using. And what this shows is consistent with the pattern of a sediment-starved delta. The blue area in the middle, this is the main Indus River mouth, which you might be able to argue probably has still has a sediment supply to it. But if you know a little bit of the system here, Kotri Barrage is the last barrage on a heavily engineered river system of the Indus River system. It's a few hundred kilometers to the north, and no water flows to the sea from the Kotri Barrage, south of the Kotri Barrage, for about 140 days of the year. So when the delta formed over geological time, of course, the delta formed from a supply of sediment from the entire Indus system. But due to these engineered structures, it's cut off the sediment supply. And although there's been no real scientifically rigorous, large-scale or recent estimates of these topography changes in the delta, there are a few references. What we saw was consistent with some of the rates that we would observe in other deltas. So when you look at the literature, it is known that the Indus Delta is starved of sediment, and this is quite an interesting plot which shows below this black dotted line, these are examples of deltas where those deltas are in sediment starved status or situation. Above the line is deltas that behave more naturally with a sediment surplus. And the gradation of the colors is an indication of the population living on those deltas. So what you can see is as we move from the upper left down to the lower right, an increase in population. Likely human influences on the delta system causing starvation of decrease in sediment supply to the delta, and a lot of the world's great deltas are sinking due to lack of sediment supply. Indus is particular of interest here, obviously because it's our study site, but it is one of the higher, one of the more populated deltas in the world. Karachi owing a lot to that. So what is the influence, or what is the consequence of that? Well, we know that we have estimates of sea level rise based on observations, but also in terms of our projections. The Karachi tide gauge in one state or another has been in operation since the early 1900s. And based on those observations, the rate of sea level rise at the Karachi tide gauge is in the order of 2 millimeters per year. If you look at other deltas around the world, the Mekong is subsiding at around 1.6 centimeters per year. The Ganges is sinking at a rate of 0.6 centimeters per year, or as high as 9 centimeters per year in places. Some literature from the Indus suggests a subsidence rate of about 1.3 millimeters per year. Our analysis, admittedly desktop, was consistent with that. And in some places, we think that based on this desktop assessment, the rate of sinking of the terrain in the delta is in the order of 5 centimeters per year, again, consistent with other deltas. So not only do you have this effect of rising sea levels, but it could be that at present day rates, the rate of subsidence or decreasing of the elevation of the terrain on the delta is actually more significant than sea level rise. Now, that may change over time, and we expect sea level rise to accelerate, but that's a really important consideration now, considering we don't know as much as we might about the actual rate, to start trying to observe that now so that we can make better flood risk assessment in the future. This was something that almost accidentally fell out of our attempt to validate the terrain data that we had available to the study. It's important to consider that any terrain data has uncertainty, a statistical uncertainty that can usually be quantified, and that has implications for what you can realistically model in terms of sea level rise. And this table shows that. So on the first column, we have a list of different intervals of contour topography map, with an associated example of a root mean squared error, which is a common metric for quantifying the error in a terrain data set. And then in the right-hand column, based on that uncertainty, this is the minimum increment of sea level rise that you could expect to model, and have a statistically robust estimate of what the resulting inland flooding or coastal flooding would be to that sea level rise based on that input data. Now, SRTM, in terms of RM, root mean squared error, sits somewhere around this mark. So if we are using this publicly available data set that was very valuable in its day and quite groundbreaking, even if we try to model a sea level rise of 2 meters, it's within the band of uncertainty of the terrain data itself. So in effect, if you're using SRTM to do sea level rise related coastal inundation, you may as well not bother unless you're talking about sea level rise in excess of 2 or 3 meters. Coastal DEM, the root mean squared error is more in this band. So we're improving a lot in terms of the certainty, the reliability of the results, depending on which terrain data set we're using. Interestingly though, SRTM is used to derive coastal DEM. So there are some advances on global scale data sets that can be used for this type of application. Now, I mentioned we were quite scarce in the data that we had to model the coastal inundation in the Indus Delta. So we had to do some testing to sort of prove to ourselves that the model wasn't importantly wrong, going back to George Box's phrase. So what we did here is we said, hey, okay, so we're using global scale bathy data. We have some really small channels in the delta. What would be the effect if we had the bathymetry completely wrong? And so what we did was in the model, we filled in all the channels. We basically elevated the bathymetry to a level of -1 below chart datum. So it was still constantly wet, but it allowed us to understand how changes or uncertainties, the implications for the possibility that we had the bathy quite wrong, what this meant for the reliability of our inundation models. And so taking samples out of the model, once we ran this test, it was a fairly extreme test, of course, to go up to -1 meter in all the channels. But what it showed us was that we could feel comfortable that implications for uncertainty in the bathy wasn't worryingly wrong in terms of the outputs of the models. So we have 2 transects here. The dark blue line is the artificially filled bathymetry, and the lighter blue is straight out of the bathy data that we had available. And yes, there are changes through the central part of the profile, but these changes, the implications for these changes, especially at least in terms of risk assessment and calculation of damages, weren't so important because there's not much exposure through a lot of these areas. And whereas at the end of these transects, where we're looking at the extent of the inland flooding, how far the storm surge propagates inland. There was fairly good agreement whether or not we had this uncertainty in the bathy or the wrong bathy or not. So we did a number of sensitivity tests. We looked at resolution, we looked at different resistance, which represented the mangroves, and we convinced ourselves that we didn't have anything worryingly wrong that was going to really throw out our flood hazard estimates, and we could stand by our claim that the model was fit for purpose. So at this stage, we modeled the storm surges through the mangroves. Now, how we do this in the model is that the mangroves, the vegetation has some resistance to flow associated with it. Remember, we're just looking at storm surge here, we're not looking at waves. And so we can, because we have a model, we can track the decay of the attenuation of the storm surge through the mangroves. And this, of course, would be very hard to do in reality, to take observations. There are some data sets that do that. More often than not, though, for any observational data sets that are available, you may have an offshore wave or surge water level, maybe some currents, and then you'll have the same at the inland extent, but it's very difficult to collect data through the mangroves. But by extracting these water levels through the mangroves, comparing them to rates of attenuation that are in published literature from similar studies and examples, we can also say that we're in the right order of magnitude in terms of the settings that we've used in the model and in terms of how this storm surge propagates through the mangroves. Okay, so the bathtub approach, for those of you who are not necessarily familiar with coastal modeling, the bathtub approach is very convenient and widely used, and it's an approach where you assume that the offshore or the nearshore water level is translated directly inland at that same elevation. So it's a bathtub. We're filling the bath at the coast, and we're letting that bath water just flood into the inland areas. So it's really important to consider, though, that the bathtub approach has limitations. Of course, when a surge comes into a particular area, it has momentum, and if you don't try to approach that momentum in a meaningful way, then you can overestimate how much the bath water goes inland. So we had to consider this in our modeling, and remember, Faye generated a synthetic data set of 8,000 typhoons, and the duration of which is reflected in a plot like this. We had some we were able to compare the tidal period inundation with a typical representative storm surge inundation, and they were very similar durations. So we were able to assume that a modeled storm surge behaves hydrodynamically in a very similar way to the tide that comes in every day. So if we normalize that tide, all those individual storm surge profiles, we can get an estimate of what a representative storm surge profile might be. And so then we superimpose that surge on a tidal signal. And we can do that in the first case I'll show you is dynamically, where the water goes in and out at the extreme, the sea level at the coast goes up and down at a certain period, and we see what the result is in terms of the penetration of that surge inland. And so we warm the model up over a few tidal cycles, and then we hit the coast with our extreme sea level. And this is what that looks like in a 2D model. So you may or may not be able to see the time step here. The peak surge event occurs at 0500 hours on the 23rd of January, so in about 48 hours from this time step. You can see the tidal inundation going in and out. The model is warming up. This is what happens every day on the Delta, but in a few hours around now, we have the storm surge event. But once the peak of the storm surge event hits, you can see that back at the open coast, the ebb cycle of the tide starts to come into play, and the water recedes, and there is a limit to how far the penetration of the tide goes. This in contrast with the bathtub effect. So if we do another test with the model, and once we hit that peak sea level, what we did was we kept the water level at the coast at that level to see what the change in inundation was. And what you'll see is fairly dramatic if you can remember back to the graphic that I just showed you. There really is, in this situation, no limit to how far the water goes, or the limiting factor is really the elevation at the coast. And that's not really reflective of reality in this case, because we have such a vast, flat area with low elevations, many tens of kilometers inland. You can see here that the inundation really just goes on almost forever, and it's a gross overestimate of the coastal flood hazard risk. When we compared these results to aqueduct floods, for example, the 100-year storm surge were very comparable, but aqueduct underestimated the 2-year and those more frequent events quite significantly, and then overestimated the more extreme events quite significantly, which is what we would expect. So just to wrap up for me, before I pass back to Faye for the last section, we just covered some pragmatic ways that we went into proving to ourselves that the model wasn't importantly wrong in a few key ways with respect to sea levels, the dynamic versus the bathtub effect, and some of these key considerations. Over to you, Faye.
Do you want to bring up our second poll, please?
Oh, yes, thank you. Yep.
Action. Thanks.
So, Catagonia, thank you. So the question being, how much would you agree with the statement? Coastal flood risk guidance is sufficient in my home country. So in a lot of countries, coastal planning policy is quite robust. In some countries, it's not well utilized, but usually in most geographies, there are some coastal planning policy and coastal flood risk guidance, which is used to help implementers apply different approaches and different policy consistently.
Do you want to close the poll now and we'll have the results, please? Yeah, so it's kind of what we maybe suspected, that a lot of people in general disagree that it's not very it's not sufficient, and there isn't enough guidance on how to assess the flood risk, which is what we found when we were doing our studies as well. Okay, you can close that poll now. Thank you. So the next part of our presentation is about capacity building and trying to help people to be able to assess the risk themselves. So this section focused on work in the Philippines, as capacity building wasn't in scope for the Pakistan. So in the Philippines, I worked with Pagasa to calculate extreme sea levels for one region, and the aim was that Pagasa can now do it for other regions, and they can use this data to perform inundation risk modelling. So the image is just me with some of the team that I work with at Pagasa, and the image in the bottom right shows you the area that we calculate extreme sea levels for. So there's two areas, Iloilo and Haloa, but you can see that's a very small part, that stretch of coastline of the Philippine coastline. So there's lots more areas that they need to know about the risk in. So the split of the work was that Pagasa provided the tropical cyclone event set. Oh, could you go back? Sorry. Thank you. And completed the hydrodynamic storm surge modelling using their forecasting model. And then we did the training on the methods and codes to assess the astronomical tides, mean sea level anomalies, emulate storm surges, and calculate extreme sea levels. So next slide, please. A big challenge to doing capacity building was obviously COVID hit. So fortunately, I was able to go out and we were able to work together at the start of the project, but it prevented in-person training later on in the project. So instead what I did is deliver the training remotely via Teams, split each training session, split the training into 6 sessions instead of, I probably would have gone and obviously worked in person over a shorter period, but we actually did the sessions over 4 weeks in the end, about an hour and a half session each time, 6 sessions over the 4 weeks. I made use of just sharing our screens, both for me presenting, but also for students doing exercises, because it was like an exercise-based training session. There are actually several benefits of running the sessions in this way. It gave attendees a chance to run codes in their own time between sessions to gain a better understanding, get more out of Q&A sessions, which I would say was the biggest advantage. That I think just having more time, because it was over 4 weeks, to really get into it means people got a lot more out of that Q&A. They came with questions that problems that had happened while they were running the codes or things they didn't understand. I think that helped a lot. Obviously, it was also cheaper, it had lower emissions, and it removed travel time from the project. So I'd say it worked well for this group, but we had previously worked together, and also we all had a high level of the same language. However, I would say, like, lessons learned is it worked well for us, but it might not work as well in other situations, because it's more difficult to gauge if you need additional explanation, speed up, as you can't see everyone. It's also more difficult to bridge any language barriers. And finally, is obviously to participate, you need a good internet connection, which not everyone's got. So I'm really pleased with the capacity building we did as part of this project. I completed the training in September 2020, and then I contacted the team at Pagasa recently to get some feedback on how the training had been used since then. And they've used the work in a few ways. The first one was to improve hazard maps. So in the project, Pagasa provided the synthetic tropical cyclone dataset. And as part of the work, we did some checks on this for suitability to use to drive the storm surge modelling. And we identified a bias that we then created a method to correct. And Pagasa have reused this corrected synthetic tropical cyclone dataset to reassess the wind hazard for the 2020 hazard maps. And then another outcome is one of the key goals of this work. Oh, sorry, if you could just go back for us, Blair. One of the key goals of this work was that we would do the extremes for one location, but then Pagasa would be able to use the codes again and the method again for a different location. So I'm really pleased to say that Pagasa have now obtained funding from the GCF for a project on impact-based forecasting, and they're going to use the training they received to assess storm surge risk for Palo Lake, which is near Tacloban Lake. And finally, one other outcome as well is that I train staff at Pagasa, and they've continued to share their knowledge. And this is just an example of this. So Jimmy, who's in the top right here, attended the course that I gave, and then he used some of my material and the knowledge he gained from it to give a lesson on extreme sea levels to meteorology master students from the University of the Philippines. And that's all our slides. Thank you very much for listening. I think we've got time for some questions now.
Thank you, Faye, and thank you, Blair, for a great presentation. It's a very relevant topic to be discussing today, being the World Water Day. Now, from here, we will move to the discussion section. I just wanted to remind you that you can submit the questions via the chat box, or you can also raise your hands in the Zoom feature, and we will unmute, give you a chance to unmute and share your comments and questions. We have a first question from Wesley in India, from Wesley from India, that says, based on modeling studies, have any flood risk management guidelines been developed to recommend demarcation of no development zones along the coast and the coastal river banks for protecting coastal wetlands? Ray, perhaps you would like to answer this one?
Sure. The simpler answer is within our study, no, we haven't. No, we haven't developed guidelines for that within our study.
I think there are more and more, I think, international sort of guidance notes that are coming out from various NGOs that talk about risk assessments in general, or coastal zone management in general, but often it's down to individual countries, even jurisdictions within an individual country, to determine the most suitable approach that is to be applied in that jurisdiction. I think that makes sense in some ways, in a lot of ways, but it also means that you see some inconsistency in terms of how different policy and different methodologies to establish setback zones and the like are implemented, not only from country to country, but within a country and actually over very small spatial scales. So that is a little bit of a problem.
Thank you, Blair and Faye. Next question is from Mark from the Philippines. And he says, from your experience on several coastal projects that you have undertaken, what's the average recommended setback or easement set on coastal areas, urban or rural?
I would say that you can't have an average setback. It doesn't, it's not really relevant to have an average value. The two important things for knowing how far setback you should have are knowing the topography of your area and also the extreme sea levels as a basic guide as the first place. So the reason I would say you can have an average setback is it really depends on, the topography of how steep it is. But then also, so your extreme sea level risk will vary around the country, but maybe not so much as your topography might vary a lot more. And obviously in steeper locations, it just doesn't need to be as far back as in low-lying areas.
Yeah, again, in different places, common practices are to use increments of different mechanisms that you use to calculate an overall setback. So of course, in every location, the tide's going to be different. In every location, the storm surge hazard is storm surge risk is going to be different. And within a policy framework in a certain place, those different increments will be applied in different ways to different settings, whether or not the overarching strategy is one of hold the line, or whether there is room to move and retreat is the overwhelming policy paradigm in a certain place. So these are complex issues that are resolved at more local scales, and sort of blanket distances and increments are very rarely applied, I think.
Thank you. Next question is from Dr. Latford Raman in Bangladesh. How can we monitor nature-based solutions regularly? And what will be the best mitigation or adaptation natural-based solution options?
Monitoring coastal ecological assets has different aspects. If you're just talking about the health or the extent of mangroves or seagrass beds or coral reefs, a lot of the time now this has been based on earth observation, but also a lot of the time some of those observations need to be validated by in situ surveys of the quality of the ecosystem. So if that, maybe that answers part of the question, but in terms of sorry, what was another part of the question?
Yes, the second part of the question was, what would be the best mitigation or adaptation natural-based solution options?
Yeah, again, it's very much site-specific and can also have something to do with the policy that's been implemented in the location. So I'm based in Singapore. Singapore, obviously a highly urbanized environment, but there are highly urbanized coastal settings in our region. Often land might be too valuable to just give up. So a hold the line approach might be dominant. And in such a policy sort of position, implementing nature-based solutions may not actually even be possible because the land doesn't exist to do that. So so hard structures will dominate, and engineered solutions will dominate over soft solutions. But in places where there's an acceptable amount of residual risk that can be tolerated, then nature-based solutions are maybe more conducive into that particular location. So it all depends on the context. I don't think can ever be a one-size-fits-all policy.
Thank you. Next question is from Krisha in the Philippines. What software can you recommend for hydrodynamic analysis for design of coastal structures?
I'll let Faye answer that one.
Well, yeah, it's quite a range of scales that we use. It depends. For design of coastal structures, it's quite different, and maybe you want to do some of the CFD modeling that Blair was showing earlier. But if you're just wondering about your extreme sea levels to implement your design of your structure, then yeah, we used Telemac offshore to do the storm surge modeling, for example. But there are multiple versions of that type of software, like the mic packages as well. They're all quite similar packages, to be honest. I wouldn't say there was an advantage, particularly one or the other, but it's more the type of package. There are packages like that that are good for, yeah, modeling your storm surges and getting your extreme sea levels offshore. And then it's about the scale you're modeling. If you're modeling specifically a sea wall and the impacts on that, maybe the pressure, etc., then yeah, you might want to do CFD modeling of that small section. And then we use the headcrest model for the inundation, for example, just because it's nice to put the features in especially for such a large area like the Indus Delta when we were doing that. So it depends probably the size of the region, what you're looking to get out of it.
Yeah, just add and agree with you, Faye, in terms of the various modeling software. There's a lot of available stuff, open source and commercial, that you have to pay a license for. But a lot of the equations that sit behind the modeling software, various different packages, a lot of them do very similar things. The interface changes on some of them, and maybe you might pay for having that nice user interface and that experience of not having to write code to change the model. And some software are supported, funded by those commercial licenses, and that funding goes into developing new features that every few years come in to a new release of the software. But a lot of the things that we use software for, a lot of the equations and the methods have been around for a really long time and don't actually change that much from package to package.
Thank you. Troy in South Korea would like to know if you can include in the model simulation the condition of the infrastructure of the city, such as the urban drainage systems or sewer systems.
You can definitely include the drainage systems. Whether you can include the quality, the way we normally include the quality is to run different scenarios. So like maybe a blockage scenario where you might block your drainage by 50%, for example. So yeah, you can't like dynamically include the condition of it because you don't know how it's going to evolve. So rather you would do like sensitivity testing, similar to what Blair was showing for, we don't quite know the channels. So you could add that drainage network and then you could say, we're not sure if it's going to work at 100%. We think maybe more, let's see what happens if, yeah, it's half blocked or, you know, only 70% of the capacity is there.
Yeah, and just to expand on that a little bit, Faye mentioned modeling different components dynamically. Often we will set up and run completely different models for completely different parts of the system and run them in what we call a decoupled mode, taking outputs from one and feeding them in as inputs to another. And I think for coastal flooding in an urban environment, if you're actually interested in a high level of detail in terms of how the drainage system handled the increases in sea level at the coastal boundary, I can't imagine very many situations where that would be done dynamically, coupling the marine model with the inland or with the urban drainage system model. You'd probably more likely have sort of coastal boundaries generated by the coastal model that the outputs of which would be used as inputs at the downstream boundary for the urban drainage model, for example.
Thank you. Another question from Margaret in the Netherlands. Have you seen certain countries or cities use the results of the coastal flood risk modeling to create organized evacuation plans for tropical cyclones in particular?
I haven't seen, so we didn't use our results in this way, but I know in the Philippines, previous to us working on this project, there is mapping available for different sea levels. The problem was we didn't know like how likely. So there is a map of where we'll inundate, for example, from a 3-meter sea level. It's just nobody was sure how likely that 3-meter sea level is to occur. But the maps that show like these different sea levels and where would inundate have been used by the disaster risk management authority to make plans of where is going to be affected, where can we go, and to make evacuation plans. So it has been used. They just wanted more information. I guess the next step is have more information on how likely these different scenarios are to happen.
Thank you, Faye. There's a question from Anne. How can we ensure that policies and development initiatives and projects are informed by coastal flood risk assessment? Take the case, for example, of Tacloban Lake after Hayam. After a couple of years, the settlement along the coastal areas inundated during the Hayam were back.
It's very difficult. The operative word in that question, I think, being how do we ensure? Well, the policy part is one part of it, but the policy can't ensure that people won't want to live there. Just like actually enforcing the policy wouldn't necessarily completely ensure that someone wouldn't see it worthwhile to inhabit that at-risk area, even just for a few months before they were kicked out. So it's very, I think the answer is it's very difficult to ensure that any sort of unplanned development would occur, especially in urban environments where, and especially in some of the countries in our area of interest are with respect to sort of informal settlements. So yeah, short answer is I'm not sure that we could ever ensure that policies alone or enforcement of policies would result in a well-executed urban planning environment.
Thank you, Blair.
But I think last week's talk talked a lot about this, which I think is the recording will be available on the website, I believe.
Yeah, that's correct.
Do you mind if I jump in and add some comments? I mean, we did discuss this last week, particularly with Ian Munt, whose expertise is in urban planning. You have to ask the question, well, why? Why do people want to live in that area? One is historical reasons. It's kind of where their families is and they've got their heritages. The other is economic reasons. Perhaps they earn their living from the sea and it's convenient for them to live in that area, to be close to where they can launch their fishing boats and so on. Or it's just cheap land that can be occupied. It's provides access to the commercial centers. And so those economic and social drivers are very, very strong, and a simple it's easy enough to develop a regulation. It's a lot harder to enforce it when you've got those kinds of those drivers. So and it comes down to everything has a cost. So you could have a policy of coastal retreat, as Blair has mentioned, but there's a huge amount of cost associated with that in terms of what impact it creates for people, but you've got to balance that cost against the risk. I mean, if people want to take a risk, people will tend to do that, and so therefore, what is the solution? The solution is either to build a gigantic seawall to protect them, or to provide some other means of forecasting and warning and providing response capacity as well. So it's a balance of all of those things, which will inevitably happen. But prevention through regulation is not always easy. It's often desirable, but it's not always easy. And so therefore, when you can't do it, you need to balance it with other measures as well.
Thank you all. Harriet in Ghana would like to know what's the background that she needs to study coastal flood risk assessment if she's a prospective student.
Do you want to take this, Blair? I feel like people come into coastal flood risk from a few different perspectives, actually. I guess we could give ours maybe. So I actually studied a bachelor's in mathematics, which is why I guess I focus quite a lot on extreme sea levels. But I also then did a master's in mathematical and numerical modelling of the atmosphere and oceans. So it's really about how you build climate and weather models. And then I worked for, I just got experience through working as well in different institutes within the UK. So there are lots of different, everyone I've worked with in this field though comes from different kind of different backgrounds, and I think that's really useful because there are lots of different challenges on the coast. So some of us are mathematicians, some people studied oceanography, and I've worked with a fair few geologists as well for the coastal erosion side of it. So there's a few different backgrounds. I guess the obvious one is maybe oceanography. What would you say, Blair?
Yeah, no, I agree that people that we work with that specialize in this come from often a wide range of backgrounds. I did do physical oceanography to a master's level. It wasn't, I think Faye therefore has a stronger mathematics background than I do. So I would look at a situation less in equations or less in terms of the technical aspects of the mathematics behind the methodologies, and more about the processes. My coastal oceanography masters was much more process based. We went on field trips along the coast for days, looking at different coasts and talking about what we saw and why we saw it. So that's a slightly different background, and you can go sort of even further away from the mathematics and be more like a coastal geographer. So wide range of backgrounds. The maths certainly, you can't go wrong if you have a maths basis and move more towards a understanding of processes. It's a little bit harder, I think, to maybe go the other way.
Thank you both. Next question is from Lito in the Philippines. Is the analysis on impact of a storm surge and tsunamis the same? Only modeling for a storm surge has been presented in this presentation.
Yes, I didn't add about tsunamis. Once you get to the stage of knowing how large the tsunami wave is, you can model it with similar software to do the inundation part of it, to work out where we'll be inundated. So that part of it and some of what Blair presented is quite similar. But the part where you're deciding, like, what is the extreme sea level, what is the risk, which I was describing, is totally different, because obviously the processes that generate tsunamis are totally different. They're not by the tides, they're not by meteorological events. And so, yes, understanding that if you want to know how likely it is to occur, you have to understand, how likely is the process which causes the tsunami. So maybe is it earthquakes in your location that are going to cause a tsunami? What are the risk factors that could cause it? How likely are they? Which the science itself is, is not maybe as robust as these more frequent events that happen from meteorological storm surges.
Yeah, I completely agree. And it's one thing to model the tsunami wave once you know what the surface displacement of some tsunamigenic event is. Once you know things about hydrodynamics and the types of models that you're using, you can propagate that displacement into a certain location. Deciding on the scenario of displacement that produces a tsunami is, seismology and plate tectonics and things that coastal oceanographers don't necessarily know a lot about. But in saying that, a tsunami event in a certain location, a really big one is something like a 1 in 4, 1 in 5, 1 in 600 year event. These events have not been well observed, and there are approaches to approximating how frequently a large seismic event might happen in a certain place. And then you can make some assumptions, broad assumptions, because it's so uncertain, about the nature of that displacement that you use as a time step 0 in your tsunami model, in your hydrodynamic model. It's generally a bit of a mix, in my experience, it's generally a bit of a mix between scenario based and understanding something about the probability of the event, to sort of come up with a scenario that's based on some statistical robustness, but comes with all sorts of caveats.
Thank you both. Next question is from Jennifer. Will it be economical to pursue a no-build zone along coastal zones where communities will be displaced based on the 100-year modeling of storm surges? Perhaps Jeff Wilson from the Asian Development Bank would like to comment on the resettlement safeguards and ADB projects for flood risk management.
Yeah, thanks, Lorena. I'm not sure whether I'm going to answer your question directly, but ADB does have a safeguards policy statement, and resettlement is a key part of that safeguards policy statement. And in general, we would be looking to eliminate or at least minimize the need for any resettlement with an ADB project. But there are examples where there will be some resettlement, and the safeguards policy outlines exactly what ADB would need to do in those cases where resettlement is necessary. The safeguards policy is being revised at this time, and the new revised safeguards policy will be out perhaps at the end of next year. But if you're interested in understanding the resettlement criteria for ADB projects, I can refer you to the safeguards policy. It's on the website, it's transparent, and it will be followed in all ADB projects. Thanks.
Thank you, Jeff, for picking that one up. There is another question from Wesley that says, can you suggest a sustainable method to tackle the erosion of beaches near the mouth of rivers with sediment depletion?
A lot of the questions are sort of broad, and in any problem that we have at the coast, it's very much something that usually you have to consider the local context very much. So what is an appropriate way to stabilize a river mouth? Well, what kind of sediments are there? What sort of development and infrastructure is there? What is the policy around developing solutions for that in that location? Is it a port? Does it have to be navigatable at all times? How dynamic is it? Is it that much of a problem? So many different aspects to looking at a particular place need to be considered. It's never a one-size-fits-all policy, but often at a dynamic river mouth, especially if it's one that has to remain stable, you'll see some stabilizing structures put into place. They have to be really carefully designed. The more sediment through flow that you're talking about, because of course you will do that, you'll develop that intervention at great expense. And if you then are further developing your port just inside the inlet, for example, you rely on that investment to keep that port operating. So do you even encourage an intervention in that place at all, or do you decide to move the port? Lots of variables.
Thank you, Blair. We'll have one more question before moving to the closing remarks. The last question is from Dr. Latfur in Bangladesh. How were the coastal models results validated with real-world observations?
Yeah, this is always a hard one because of the data availability. So the storm surge modeling in Pakistan, for example, we did comparisons for the observed typhoons that we had, and then you have to use the data you've got. Do you know what I mean? We had we did have gauges at Karachi, but mainly it hadn't hit that one specific gauge that's quite far north in our area of interest. So instead we looked at how far it inundated, what type of depths it inundated at, and compared them to knowledge in the news, for example, of which communities have been affected. So we used some of that type of information to validate the model. We did look at whether you could use any satellite data, but unfortunately, you know, coastal inundation is, like I said, it is quite fast compared to maybe riverine flooding, and it'll come in and then it also starts to drain out on the low tide. So you need your satellite to go above it, right, as it's like hitting your maximum extent or whatever. So it pretty much never does that, unfortunately. So we weren't able to use that data. But yeah, we've used tide gauges where we can. We've even used short deployments as well. So like if we've been using satellite data, I use satellite data to characterize the astronomical tides, and then use short-term tide gauge deployments to calibrate and validate that data. So we had some in situ. So we tried to make the most of every single data set that we can get our hands on, really.
Yeah, and another important note about the surge component of any observation of a coastal flood. Take Karachi, for example, with a 3-meter tide range. Often the surge that comes in might be sort of buried in that band. So in that particular case, with a 3-meter tidal range, you know, if the surge occurs, you have a 2-meter surge, but it occurs at low tide, there is no coastal flood. You can't observe it in a satellite image, even if the satellite was passing over at the exact instant of the peak of the surge. So it's quite hard to differentiate between the different components. And that's why models are so handy, because you need to isolate the different components, sort of look at them all in isolation, and then use statistical approaches to bring them all together again to come up with a statistically representative extreme sea level. So that's a challenge as well. And also, finally, it's also difficult. Satellite imagery, which shows areas that are wet during a storm surge event, will show areas that are wet because of the storm surge, because of the tidal inundation, but also because of the surface water from the rainfall inland. So it's very difficult to isolate those different components in an image as well.
Thank you. With this last question, we close the discussion, and I would like to invite now Ian Wood for the closing remarks. Over to you, Ian.
Look, thanks to our presenters for your presentation. I'm sure everyone agrees it was fascinating. There was a lot of information in that. And thanks also to everyone who participated in the discussion, gave us some good questions and good ideas to think about. And what we could see is many questions go beyond just the science and the mathematics of coastal analysis, but into the social and policy issues of what to do, how to respond. Some of the things that I'm just going to mention that we learned during this discussion. One is that sea level rise is inevitable and clearly an emerging and growing and very serious issue. Two is that data is still very scarce. It needs to be specific. It needs to be accurate. Many of these global data sources carry a lot of uncertainty, and if we're going to address climate change issues, we really need that good data. Three, we learned that all models are wrong. Perhaps we knew that already, but it's really important to understand not to be importantly wrong. To be wrong unimportantly was a key challenge, I think, for everybody who's working in this field. And number four, what we learned was that more than half, maybe about 2/3 of respondents indicated that coastal policy and protection standards is inadequate in their countries. And so you combine all of those things together, we've got a real situation, we've got a real problem emerging now, and just only getting worse with more development, more urbanization pressures, higher population growth, greater demands for environment. Combine that with sea level rise, combine that with typhoon intensity. There's a lot of issues coming together, creating potentially very big problems. And so why isn't a coastal policies good enough? Well, one is perhaps that it's difficult. This kind of analysis that we've talked about today takes a lot of time and a lot of effort and a lot of data which we don't have. And secondly, is that the problems are just very large. They're just difficult questions to answer and provide solutions for. But this means that we should be trying harder. So, I think everybody who's participated in this webinar has some role to play in continuing this conversation in your workplace and in your circle of colleagues to ensure that there is this continued emphasis on understanding that these big issues exist and understanding that that policy solutions and real life solutions are still required. So that were my takeaway points from this. And so once again, thanks to the presenters. This is number 3 out of 5 presentations that we're doing in this webinar series. And so I'll introduce what is going to be next week, which is also very interesting on a different tack though. So next week it's about economic and finance for IFRM. And so we have 2 presenters, Jane Tutil and Guillaume Dulac from JBA and Land Mills respectively. And they're going to be talking about the issues for economic analysis based on some of the work we've done in this project. What we found was that economic analysis was poorly addressed in many flood-based projects, and understanding that is a really key issue. There's a lot of interesting things from that. And secondly, Jane is a specialist on insurance and flood risk management issues. And so we're looking forward to hearing from that. So please join us next week to hear about these topics. Thanks. Thanks, Lorena.
Thank you, Ian. I just want to remind everyone that it will be the same time, 4 p.m. Manila time, but due to the daily saving time, it will just be an hour later than usual in Europe. We hope to see you then next week, and thank you everyone, and goodbye.
Thanks, Lorena and team.
Thank you.
See you next week.
Thanks.
Bye.
Thank you.